Quantum mechanics, a word that everyone knows and one of the most important theories in physics. In this video, we'll use the idea of the wave-particle duality to show why we actually need this theory. So, why would we think of light as a wave? Well, one of the most important characteristics of waves is that when a plane wave enters a slit, diffraction will occur. And in 1803, Thomas Young proposed the double slit experiment as shown here. So what happens is that a plane wave encounters a slit and then diffraction will occur. So diffraction is basically the spreading out of the waves. So if we look at the image here, we've got two slits and a plane wave coming in from that side. So the waves will be spread out and it creates like different parts. So we've got part 1 and part 2 here. And if we call this angle theta, then this distance, just basically the path difference between the two waves, will be d sine theta. So what we can see is that if the path difference between part 1 and part 2 is an integer number of wavelengths, we will have constructive interference. The n stands for an integer, that is the wavelength, and is the path difference. If we have the path difference equals to a non-integer wavelength, then there will be destructive interference. So constructive interference can be explained by looking at two waves. So we've got one wave here and one wave here. They're in phase, so when you add them up, the amplitude will increase. So that's why we see bright fringes on the screen here. When we have destructive interference, we see that the waves are actually out of phase. So one wave here, one wave here. When you add them up, you actually get 0 because they both cancel each other out. So this is where we see a dark fringe on the screen. So now we can see how this works in practice.
This is our double slit experiment here. This is the laser which provides the light source and a diffraction grating to access the two slits. So when we shine the laser light through the diffraction grating, it forms an interference pattern seen on the wall over here.
In early 1920s, Arthur Compton, who was interested in X-ray scattering, found out that when a photon hits an electron, it will be deflected with angle theta and with larger wavelength. So in order to explain this increase in wavelength, he assumed the photon as a particle same as the electron. Also, he considered the collision between the photon and electron as an elastic collision, where the energy is conserved as well as the momentum. So since the energy is conserved, when the photon hits the electron, it will transfer parts of its energy to the electron, and therefore it will end up with less energy. So according to the equation for the energy of photon, which can be also written in terms of lambda, when we have decrease in energy, the lambda should increase. And that's why the lambda of the photon has increased after the collision. We can also explain this change in wavelength of the photon using this equation, where delta lambda is the difference in the wavelength of the photon, and lambda c is Compton wavelength, and this theta here is the angle by which the photon has been deflected. The Compton wavelength is equal to h divided by m of electron times c, where h is the Planck constant, and c is the light velocity, and m of e is basically the mass of the electron here.
We've seen that waves can have particle characteristics, so why can't particles have wave characteristics? Louis de Broglie, in his 1924 PhD thesis, made the hypothesis that the concept of wave-particle duality extends beyond just photons, but to any particles, i.e. all particles have wave-like characteristics. A photon of light has a momentum given by p is h over lambda, p is momentum, lambda is the wavelength. So de Broglie's idea was to rearrange this to for lambda, i.e. lambda is h over p. This gives the associated wavelength for any moving object. Given that the classical momentum for an object is p equals mv, the de Broglie wavelength of an object is inversely proportional to its mass, which means that for most objects it's very small. Take a person who's running, for example. Let's say they weigh 70 kilograms and are running 10 meters per second. Using de Broglie's formula, we can work out their wavelength. 9 times 10 to the negative 37 meters. This is an absolutely tiny wavelength, which is why we don't see people exhibit wave-like properties such as diffraction when they run through a doorway. But for objects of much smaller mass, these properties can't be seen. Electrons, which have a much smaller mass, therefore have a much larger wavelength. which means we can repeat the double slit experiment using electrons, as seen here. You send an electron beam through to a slit, you get the characteristic interference pattern. But you may wonder, how can particles such as electrons interfere with themselves? So what you can do is you can send the electrons out one at a time, and you still observe this interference pattern, which must mean the electron is interfering with itself. But if you decide you want to find out which slit it goes through exactly by adding some sort of measurement device, you will find that the entire interference pattern disappears, leaving behind just two peaks in intensity where what you'd expect to see if you had two particles going through the slit. So this strange result where apparently measuring the system can change the outcome cannot be explained through any classical theory, and actually the fact we've seen matter acting like waves and light acting like particles, this was the reason why we needed a new theory to describe the universe around us, and this was quantum mechanics.